We continue with the series. Now we introduce geometric series. Those are some of the series for which we know how to compute the sum, and we know when the series is convergent and when it's divergent. So geometric series has the form an argument times a ratio to some power. So usually we start at 1, but we could, in certain cases, start at 0 or 2 or 5, depending on the situation. What is important is to write out the geometric series. This will actually help us much more than the form itself. So the first component is when n is 1, so this is 0, r to power 0 is 0, right? No, it's 1. So a times 1 is a. Then we have a times r plus a times r squared plus a times r cubed, etc. So we see the shape, and that's what matters. We have two components here, argument a, that is important, and the common ratio r. So those are the two important components, you will see why. So what we know about the geometric series, and that's why we like them, is when the common ratio in absolute value is smaller than 1, then the geometric series converges. So that's good news, we know it immediately. And the sum, also we know what's the sum. We have a formula. It is a, our argument, divided by 1 minus r, r being the common ratio. Obviously when r is smaller than 1 in absolute value. On the other hand, if r in absolute value is bigger than or equal to 1, the geometric series diverges. So this is the good news. Geometric series, we know exactly based on its common ratio, we know when it's convergent and when it's divergent. In the case when we have convergence, we also know what's the sum. So this is super important. It is given for free. So let's see some of the examples. Here we have a sum 1 over 2 to power k. So I'll just write the terms. So for k equal 1 is 1 to power 1 over 2, then 1 over 2 to power 2, plus 1 over 2 to power 3, plus 1 over 2 to power 4. Don't compute it, just write it out. It's much better. You will see why. 6, and we keep going. So the shape of our geometric series is the argument, and then plus argument times the ratio, plus argument times ratio squared, plus argument ratio cubed. So what we need is to identify the first term, that is our a, so that's 1 over 2, and then we need to factor it out of the next guy. So here we have 1 over 2 times 1 over 2, right? So we have a, and this is r. So immediately we have everything. So here we have something like this. So this is 2 to power 3, 2 to power 4. I split it in two pieces. So this way, if I write it, it's much easier to see what's happening. Here, a is the first term, right? And this is a. And we see it again here, and again here, and again here, and again here, just like the shape here. And the second component is r, which is 1 over 2. Now, from the results here, in geometric series, when the common ratio r is smaller than 1 in absolute value, we know that the series is convergent. So we can immediately say here, since r equal 1 over 2 is smaller than 1, obviously we need absolute value, but here we have 1 over 2, so no need for absolute value in this case. Then the geometric series is convergent. So we know that, we don't need to prove anything. And the sum of the series is, so the sum is given by A divided by 1 minus R. So that's why we need to identify both of them. So A was 1 over 2 divided by 1 minus R. R was 1 over 2 also. So we have here 1 over 2. 1 minus 1 over 2 is 1 over 2. So this is 1. So the series 1 over 2 to power k from 1 to infinity is actually equal to 1. It is a convergent series. So that's cute. So that's how we do. First thing is to realize what is our first element and then factor it from the second one. So that way we have the A and then we have also R. This way it's much easier to see what's happening. So let me try another example. So these geometric series are super important because those are one of the rare series where we are able to easily compute the sum when the series is convergent. So let's say I have a series 3 over 5 to power k. So let's say this time I start from 0, doesn't matter. So I have here 3 divided by 5 to power 0, 3, 5 to power 1, 3, 5 to power 2, 3, 5 to power 3, and we keep going. So first thing we can notice, we could actually factor 3 out. That would be something useful. We don't have to, but it could be useful. So here I factor 3. So 5 to power 0 is 1. So, and then I have 1 over 5 plus 1 over 5 to power 2 plus 1 over 5 to power 3. Right? I factor 3, so the 3 from all the upstairs is taken out. So now what I observe here with this geometric series is that I have a factor in front, that's fine, there's nothing problematic there. I have A here. So here A is 1. 1 times 1 over 5. 1 times 1 over 5 squared. And then R is 1 over 5, which is also smaller than 1. Therefore, our geometric series will be convergent. So this thing is smaller than 1 in absolute value. Then the geometric series always be careful regarding the starting index. Is it 0? Is it 1? Things change a little bit depending on the situation. So here I have A and R, so this series is convergent. And the sum is, so what do we have? We have 3 times, and now this is our geometric series here. A is 1, so I write A divided by 1 over, divided by 1 minus R, so I'll just replace. So A was 1, and R is 1 over 5. Now the good news is we are able to work this out to have a nice expression for the sum. So this is equal to 3. So here downstairs I have 5 minus 1 over 5. So this is 3. Upstairs here 4 divided by 5. So I have 3 times 5 divided by 4. So I have 15 divided by 4. Okay? So this is the sum of this convergent geometric series. Maybe we can have another one. So you see, if we factor something, we keep it there, we don't forget about it. So let's say now we have a different series. Let's say 5 divided by minus 4 to power k, and this time let's say k goes from 1 to infinity. So if I write out, it's always good to write out the geometric series. Obviously here we can immediately factor 5, even though we can write it, but you can factor it immediately because we see there is no k regarding the expression on 5. It's not linked, so we can immediately rewrite it. So that way it simplifies a little bit. Okay. So I have 5 times. So this series here is, we start with k equal 1, so it is 1 over negative 4 plus 1 over negative 4 to power 2 plus 1 over negative 4 to power 3. I keep the form. There is no point of writing here 1 over 16. There's no point of doing that. Just keep the form. What we want is to identify the first term, and then second thing we want to identify is the common ratio. So there's no point of writing the values here 16, 64. It's not going to help us at all. So here the first term is 1 over negative 4. Here I have 1 over negative 4 times 1 over negative 4, right? So this is the first term again, r. And then here I have 1 over negative 4 times 1 over negative 4 squared. And then I just rewrite a little bit to keep the same form. Okay. So now I see clearly the first term a is 1 over negative 4. And the a is repeated here. You see a, r. So r is also, in this case, this. Now, we remember that we need to check the value of r in absolute value. So this is equal 1 over 4, which is smaller than 1. This means that our geometric series is convergent. Okay, convergent. And we will find the sum now. And the sum is, so our series is, I'll write it here, just copy a little bit. Normally, when we solve problems, we don't copy this because it's just a waste of time. We know which series we are talking about. So this thing is equal to 5 times. So here, this is my geometric series. The first term, a argument, is here, and then r is here. So the 4 formula, we copy it, and then we plug the numbers. So A was negative 1 over 4 divided by 1 minus R was negative 1 over 4. I write all the pieces, then I will simplify a little bit. So I have negative 1 over 4. Write these fractions properly. So I have 1 plus 1 over 4. We don't want to make any errors here. So this is 4 plus 1 divided by 4. So this is 5 over 4. So this guy here, 4 and 4 simplify. So I have minus 1 over 5. Or if you want, you flip this on the other side. If you want, you can write minus 1 over 4 times 4 over 5. Right? So the 4 simplify, and this is equal to negative 1. So we have a convergent geometric series. What you need to realize in this case, the sum is negative 1. There's nothing wrong with it. It's all fine. There's no problem at all. What matters is to expand the writing to identify A and to identify the ratio. That's the most important with this geometric series. Another example. So let's say we have something a little bit more challenging. Obviously, when R in absolute value is greater or equal to 1, the series will be divergent. So that's important to notice. So let's say we have something like this to power n plus 1. I'll change here for n. So we have different indices just to practice a little bit with different indices. So what does this mean? I have minus 0.4 to power 2, minus 0.4 to power 2 plus minus 0.4 to power 3, right? Then the next guy is minus 0.4 to power 4. So you see I need to be careful if I start from 1, 1 plus 1 is 2, then 3, 4. So it is important to be careful at the beginning, because otherwise we have the wrong A and then it's a huge problem. So here, things look a little bit different. So this is my first term. And then my second term, I need to split it into first term times R. So I'll just copy this, and I keep it. Don't need to recompute, just keep the thing as is. So this dude here, I have A times R. So here I need to write it as this times this. So these two, power 3. And then just rewriting this part here. So power 4, I split it into power 2, power 2. Power 5, again, 2, and then power 3, and we keep going. Again, what matters is to identify properly A, and this is A again, and to identify R. We see that R in absolute value is 0.4, which is smaller than 1, which means that our geometric series is convergent. And then on top of that, we are able to find the sum. So the sum is given by the expression A over 1 minus R. So now we plug A. Oops. A is this here. Then 1 minus R is negative 0.4. So I write everything once properly. At some point we will evaluate this, obviously. So here I have 1 plus. So here I have, again, squared divided by 1.4. So we can evaluate with calculator and then get the exact value. So this is the procedure. We need to be careful where we start with the index. We always write out a couple of terms, at least 3, 4. And then we realize which term is the first term, and then we try to factor it so that we have A times R. That way we identify R also. Here, our R was given here. And then, since R in absolute value is smaller than 1, the series is convergent, and we can find the sum. Let's use another example. So these geometric series, they are really easy to work with. Just need to write a couple of terms and we are good to go. So let's say we have something like this divided by, let's say negative 2 to power n. We just write something a little bit more challenging. So here we see the situation is a little bit different. So my an is 3n plus 1 over negative 2n. I see that the exponent is not the same, so let me rewrite this a little bit. So I'll bring everything to exponent n, so this is 3 times 3 to power n divided by minus 2 to power n, which means this is 3 times, and then I have 3 over negative 2, everything to power n. That's cute. Now, how much is this? It's maybe useful to write it, just to see a little bit. So this is negative 1.5. Oh, there is something happening. So that's useful to rewrite. Then we can now write the sum, the series. So this series is equal to, I will just rewrite the term. The term is here, which is written this way. So 3 times minus 1.5. We can keep 3 over 2 with the negative sign. It's fine. Okay. So now obviously 3 multiplies everything, but there is no n on 3. So 3 can go outside. There is no issue with that. So I have something like this. So if I write it out, so 3 and then I open the bracket, now I write the series. So n starts from 1. So I have negative 1 over 1.5, that's the first term, power 1, plus negative 1.5 to power 2, because n equal 2, plus negative 1.5 and then equal 3, 3, plus negative 1 over 1.5 to power 4, plus, so we keep going, no need to write anymore. Here, my first term is negative 1.5. Here I have negative 1.5 times itself. Oh, that's good news. Okay, because now I have A then I have A times R. A plus A times R. Yay. So I'll just write another one here symbolically. And then it keeps going. So now we know from here that A is equal to negative 1.5. R is also equal to negative 1.5. Now what we see is in absolute value, this thing is equal 1.5, which is bigger than 1. Uh-oh. We have a geometric series whose common ratio is bigger than 1. What does it mean? It means that the series is divergent. So our original series, I'll write it as we did from the beginning. Any form is fine, but I'll just copy the original form, is divergent. Which means there is no sum, so don't write me the expression of the sum. The series is divergent. So we need to be careful with these things. Let's have fun with another one. So essentially this is just a practice of writing out a couple of terms of geometric series, recognizing the first term and then recognizing what is the common ratio R. Based on R, we decide if the series is convergent or not. So let's say I have something like this. So here we start from 0. So here I have minus n. So I can rewrite this immediately. Radical 2 power n. So 1 over. So now if I write it out, when n is 0, I have 1 over radical 2 to power 0 plus 1 over radical 2 to power 1 plus 1 over radical 2 to power 2. So just write a couple of terms. Okay, so let's erase this. No need anymore. So here, what do I see? This is 1 plus 1 times radical 2 plus 1 times radical 2 squared plus 1 times radical 2 to power 3 plus plus plus. So here A is 1. This guy here. So 1 times this plus 1 times this. So we have the shape 1 plus 1 times R plus 1 times R squared. So it's there. R is 1 over radical 2. It's positive. Now radical 2 is approximately 1.4. 1 over that is smaller than 1. Which means that the series is convergent. So this geometric series is convergent. Since it is convergent and is geometric, we are able to find the sum. And the sum is, so what's the sum? A divided by 1 minus R. So A was 1, R was 1 over radical 2. So we can rewrite this a little bit. So I have here radical 2 minus 1 divided by radical 2, which is equal to radical 2 over radical 2 minus 1. you can find the approximation, but normally we keep it as is. So this is a convergent geometric series, and we have the value of the sum. Maybe the last one. So let me see an ugly expression. So let's start here from 1 on. So we see that an is 7n plus 2, 10 to the power n. So we don't have the same exponent, so I'll have here 7n times 7 to the power 2. Okay, so 7 to the power 2 is 49 times 7n over 10n, so 7 over 10 to the power n. Okay, fine, so I can now write it. So it's 49 times 7 over 10 to the power n. So I'll just write a couple of terms. 49 times n equal 1, so 7 over 10 plus n equal 2, 7 over 10 squared, plus 7 over 10 to the power 3, plus 7 over 10 to the power 4, and then we keep going. No need to write anymore. 49 times. So we see the first term is 7 over 10. Here we'll have 7 over 10 times 7 over 10. So it's useful to write it. When we get more experienced, we can go faster. So this is for this guy. To power 3, we have this, and then power 2. Power 4, I will write it also. 7 over 10 to power 3, and then we keep going. So here again, geometric part. A, the first term is 7 over 10. A, R. So this is R. R is 7 over 10 also. And R, which is 7 over 10, is smaller than 1, which means the series is convergent. So the geometric series is convergent since this guy, the common ratio is smaller than 1. Now we can compute the sum. So the sum is 49 times, so this is my geometric series. A is, so I'll write A over 1 minus R. So I'll write the formula first and then I'll copy A, so 7 over 10, big division, 1 minus 7 over 10. So now we need to struggle a little bit to write it properly. So we have 7 over 10 upstairs. Now here, this is 10 minus 7, it's 3 over 10. So this simplifies a little bit. So we have 7 over 3. Okay? We can compute the exact value also, it doesn't matter. So this is a convergent geometric series, and we are able to find the exact value of the sum. So maybe last one, and then we stop, because it's always the same thing. Write it out, find A, the first term, and then find the common ratio R. If the common ratio R in absolute value is more than 1, series is convergent. We can find the sum with the formula. If it's bigger or equal to 1, then there's nothing for us to do. The series is divergent. So let's say I have this, something like this, let's say. starting from 1. Again, I write an because they don't have the same exponent, so I need to suffer a little bit. So this guy here is, so 6n minus 1 is 6n divided by 6, right? I write step by step just in case. So the 6 will go up, so I have 6 e2n divided by 6n. Now again, they don't have the same power, but I can take e to power 2 also. So this is 6, and then I have e to power 2 divided by 6, everything to power n. Now it's cubed. Fine? Why is this important? Well, the factor in front doesn't matter. We'll just move it outside the summation. But what matters is to have the same power here on the expression, because probably this will be our r, and then we will be able to decide what's happening. So finally, this guy here is equal to 6 summation n e to power 2 over 6 to power n. So I'll write it out a little bit. So this part here is e to power 2 over 6, so that's our first term. Then we have e to power 2 over 6. Then n is 2 plus e squared over 6 to power 3 plus e squared over 6 to power 4, etc. So we don't need to write. Equals 6. My first term a, here I need to factor it also, so that way I'll get r with it. So I have e to power 2 over 6 plus, so this guy here is e to power 2 over 6 times e to power 2 over 6, plus e to power 2 over 6 times, for the cube now it's here squared. Okay, no need for the rest. So now again, I'm able to identify a, the first term, and then I'm able to identify r. So my r will be this. A is the first term, e squared over 6, which doesn't play much role at this moment. Now r is here, is also a squared over 6. Now if we compute e squared, it's going to be around 7 something, so this guy obviously is a little bit bigger than 1. What does it mean? I have a geometric series whose common ratio is bigger than 1. That means the series is divergent. Obviously we need to compute this with a calculator just to make sure, but it's 7 point something. So this is bigger than 1. Geometric series is divergent. So there is no sum of this series because the series is divergent. That's the application for the geometric series.